Okay, hello everyone that's here. Uh, why is my whiteboard not appearing on the screen? Ah, that's why. Okay, 1 second. Ah, excellent. There we go. Right. Mm-mm-mm. Okay, everything seems to be working fine. Okay, well, hello anyone and everyone that's here. I can't see. Oh, hello, Olvendil. Hello. So you can probably tell from the title. Today we're going to talk about black holes a little bit. So this was the topic that was most voted for on the poll I put on my Twitter about what we could talk about today. So we are going to restrict ourselves a little bit. So you'll notice that this is called Black Hole Basics. So we're not going to talk about an enormous amount about black holes because I like when we talk about things, I like for us to talk about them in full detail if we can and try and do some proper maths and do things honestly with them. So we are going to talk about black holes, but we're not going to get to stuff like Hawking radiation or information paradoxes. We're mainly going to be sort of building up some basic stuff from GR, stuff like time dilation, and looking at the deflection of light from black holes as well. But before we do that, we'll talk a little about black holes actually in astrophysics. So I've written this down in advance because I drew some little pictures and it would be kind of boring to draw these pictures, you know, at the time. So I drew them a little bit ahead of time. Okay. So where are we? Here we are. Okay. So black holes are, they're an enormously interesting area of research. Oh, hello, Jegchin. Mod Squad indeed. And they are complicated. So there's something that's not predicted by Newton's theory of gravity, though we will talk about something similar that is predicted by Newton's theory of gravity. They're purely a result of general relativity. And general relativity, for those that don't know, is Einstein's theory of gravity, which is quite a bit more difficult to handle than Newton's theory of gravity. It involves a lot of this quite difficult mathematical machinery, things like tensor calculus and differential geometry. All of this stuff is not particularly easy to work with. So we're going to kind of summarize some of these results and talk a little bit about the motivation of general relativity. And then we'll try and apply some of this stuff to figure out some things about black holes. Okay, but let's talk about black holes in terms of astrophysics, in terms of what they actually are like in the universe. So there are enormously wide ranges of black holes that you can possibly have. In theory, there's no minimum mass a black hole can have. You could have a black hole with a mass as tiny even as the Planck mass, but the only thing is these things wouldn't last very long in terms of Hawking radiation. They would evaporate very quickly. So let's talk a little bit about some of the different mass scales you can have for black holes. There are black holes that are called stellar mass black holes. These are black holes that arise from the collapse of very large stars. So if a star has a core that is sort of bigger than around 2.17, 2.5 solar masses, if the core is bigger than that, then when the star comes to the end of its life and it'll sort of go supernova and the core will collapse inwards, then it's above this maximum size that is supported against collapse of neutron stars. So just like white dwarfs have a maximum size that we call the Chandrasekhar mass, neutron stars also have a maximum size, though the name for it is a little bit less well known just because it's quite a bit longer. But this is the so-called Tolman-Oppenheimer-Volkoff limit. And there's also a lot more uncertainty on it because calculating it is nowhere near as straightforward as calculating the Chandrasekhar mass. So it's thought that neutron stars that are more massive than this would be unable to support themselves and would collapse. So we would expect that for black holes that are formed from the collapse of stars, they would have masses as a minimum of 2.17 or a little higher, depending on where you take this bound for the Tolman-Oppenheimer-Volkoff limit to be. But I think in practice, we've never actually seen black holes that are less massive than about 3.3 solar masses. I should say that's what this M with a subscript circle dot means. That means a solar mass. So I think the smallest black hole we've ever observed was around 3.3 solar masses or something. So in theory, stellar mass black holes, this range is often quoted between 3 and 30 times the mass of the Sun. Okay? And the life cycle is very massively oversimplified here, but it looks a little like this. So you have stars that are in the main sequence part of their life, which we spoke a lot about last time. Then as they have sort of burnt up all the hydrogen and then later helium in their cores, they move on to this red giant or this super red giant branch. And then if they're massive enough, when it comes for them, when they leave this red giant branch, there'll be nothing possible to stop the collapse of the core inwards. The core will be so massive that it won't be able to be halted by electron degeneracy pressure, which is what turns the core into a white dwarf. It won't be haltable by neutron degeneracy pressure, which is when the core becomes a neutron star, if it's supported by neutron degeneracy pressure. And then it'll form a black hole, which I've kind of sketched here roughly. So black holes, although they sort of appear pretty simple objects, you know, they're black, they don't really emit anything. And remember, we're not going to talk about Hawking radiation particularly today. But actually, they can be incredibly active and incredibly interesting. So when matter falls into a black hole, because it has to conserve angular momentum when it falls in, it will often form these sort of rings or disks of spiraling in material around the black hole. And because the gravity is very strong and the black hole is very dense, these orbits can become very tight and very small. And this generates an enormous amount of energy by these disks. And then there are all sorts of complicated processes going on that can produce these jets as well, that are shot out by the black hole if it's large enough and active enough, and its accretion disk has enough material in it. And all these processes are very complicated, how these jets are actually formed, and I think there's still an enormous amount of study that goes into them, because it's not entirely known how, you know, the mechanisms that generate these jets around black holes, and how this kind of directly comes from the accretion disks. I think these mechanisms are still fairly mysterious. Okay, so those are stellar mass black holes. If we go up now to some of the largest black holes that we see or expect to see in the universe, these are supermassive black holes, which in terms of a definition we give as between 10 to the 5 solar masses and 10 to the 9 solar masses. So between 100,000 and a billion solar masses. So these are enormous black holes, really. And it's thought that these supermassive black holes, that pretty much every galaxy has a supermassive black hole at its center. And it's thought that, in fact, the formation of galaxies, how galaxies come to be in the first place, relies very heavily on the presence of these black holes, which sort of grow by accreting and taking in matter from the disk surrounding them. But again, this is also very mysterious, and people don't fully understand yet how galaxies come to form and what role these supermassive black holes play in this formation. But it's thought that all galactic nuclei, for pretty much all moderately sized galaxies, have a black hole at the center. Okay. And these galactic nuclei can be very active, just like the sketch we drew previously, where we had an accretion disk and jets coming out of, not out of the black hole, but of sort of the surrounding area around the black hole, from this very tightly inspiraling and very energetic material circling the black hole. You can have the same thing around these supermassive black holes that we'd expect to find at the center of pretty much all galaxies. And these are often called quasars, these supermassive black holes at the center of galaxies. It's thought that quasars, the things at the center of galaxies, very, very bright centers of galaxies are black holes. I think that's the only real contender for what they are at the moment, but there's not been any sort of direct observational evidence, as far as I know, that they are black holes. These could be completely different mysterious things, but as far as we know, the best explanation is that they're black holes. And if you look at the screen here, there is a slight image of one of these supermassive black holes. So this image here is a rendering of the supermassive black hole at the center of our own galaxy, which is called Sagittarius A star. So here you can see the accretion disk, this spiraling in matter, getting closer and closer and sort of denser and hotter as it gets towards the center. And then from a distance away, these things just look like very, very bright radio sources, which is how they were first detected. But when we look in, they do have, well, we think they do have anyway, a very, very small, dense center that is this black hole. And you can see this material spiraling in, and you can also see some of these interesting effects around the edge of the black hole, like this light deflection, how the material just on the other side of the black hole, the light from it, is appearing to be bent very heavily, and we'll try and derive a result that describes that as we go along later. Okay, but you can also see the jets from this thing. These jets are sort of shooting out perpendicular along the axis of rotation, and these carry enormous amounts of energy. And like I say, it's not totally known, I think, how these jets are formed and what mechanism it is that generates them. All we know is observationally that they are there, and you get jets in, other kinds of astrophysical objects too. But I think the mechanism that produces them is quite mysterious, actually, or it's not totally understood. Okay. I should also say, while we're going along, if you want to, I have again posted sort of notes in advance of the calculations we'll be trying to do on my website. So if you go to my website, which you can find in the About section, and then you go to the section that says something like Twitch office hours, I think, then at the bottom there'll be a set of notes that says black hole basics, and that'll describe some of the calculations we're going to go through today. Okay? But anyway, this is the kind of structure of a typical galaxy with a galactic nucleus and a black hole at the center of that galactic nucleus that we were just describing. So there we go. There is the Milky Way, the black hole we were just looking at there on the screen. This is a rendering of Sagittarius A star, the supermassive black hole at the center of the Milky Way. And this has a fairly large mass. This is about 1 million solar masses. It's thought to be from, observational evidence. And then there's the kind of opposite side of the scale. There are these primordial black holes, which are comparatively very tiny and could be very, very tiny indeed. The mass bound we've given here is just less than a solar mass, but many of them could be much, much smaller than that. So there's no complete evidence that primordial black holes exist. But the idea is that these are black holes that were formed very early on in the universe. When the universe was much, much smaller, quite shortly after the Big Bang, matter densities were very high. And you know that black holes are, or the way people sometimes talk about black holes, is as being these regions of sort of extreme density. The singularity of a black hole people often describe as a point of infinite density. And it's true, you do need a very high matter density to form a black hole, if it's a black hole formed by the collapse of matter anyway. So in the early universe, when you have naturally high matter densities, because the universe was a very small place when it was very young, it's not too difficult actually to form these black holes, primordial black holes. And people think they could be formed in all sorts of different ways through when phase transitions were going on in the early universe. And there's still a lot more to know about these, and these are very mysterious. And like I say, it's not even known that they exist. Okay. But we can sort of think about how big they would have to be if they did survive. So although we're not going to talk in detail about Hawking radiation, we did mention it. This is this mechanism that black holes can use to actually evaporate. They can sort of, or they do emit thermal radiation. Okay. is infinitely dense. Yes, so that's right. So you can describe the center of a black hole as being a point of infinite density. But in fact, it sometimes is a little misleading to think of it that way because you don't even always need matter to have a black hole. You can form black holes purely by curvature of space-time. So, for example, I think that people have showed fairly recently that you can form black holes just by the collision of gravitational waves or by superimposing gravitational waves. So these things, the nature of the singularity and what's inside of the horizon of the black hole is such a foreign concept. I think thinking of it as a point of infinitely dense matter can sometimes be useful, but actually it's a lot more complicated than that, and there's a lot more we don't understand about it. But yeah, thank you very much for the comment. Zoiku? Sorry, I can't read the name properly. But hello to you. So, because black holes evaporate by this process of Hawking radiation, we can place a sort of lower bound on how big the surviving primordial black holes would have to be. Because if they were any less massive than around 10 to the 11 kilograms, then the black holes that were formed very early on in the early universe, they would have already evaporated by this Hawking radiation. Okay. And then I've written down 10 to the 11 kilograms. This is about 10 to the minus 19 solar masses. So this is an incredibly tiny black hole compared to what we were talking about earlier, where we have supermassive black holes being around 100,000 to a billion solar masses, and stellar mass black holes being 3 to 30 solar masses roughly. This lower bound for the size of surviving primordial black holes is a lot smaller. It's around 10 to the minus 19. Oh, thank you for the follow. So hail UAE 2013. Interesting name. Okay. So there are lots of theories involving primordial black holes. It's thought that they could contribute to the total amount of dark matter in the universe. I don't think people really think that the primordial black holes will entirely explain all the amount of dark matter, but I think it's thought they could contribute. They could be a contribution. And it's also thought that they could change the presence of primordial black holes could speed up the rate at which phase transitions in the early universe happen. This is actually a paper published by my PhD supervisor. He first had this idea that the presence of primordial black holes might be able to contribute to speeding up phase transitions like the electroweak phase transition in the early universe. But as I say, there is currently no evidence for primordial black holes. So it could be all total pure speculation. But it certainly makes sense that they would exist. The logic is fairly sound in my opinion. So how do we know these things actually exist? How do we observe black holes? Well, there's this nice quote from the sort of sci-fi comedy series Red Dwarf, which is that the computer of the ship Holly says, well, the thing about a black hole, its main distinguishing feature is it's black, and the thing about space, your basic space color, is black. So that's a pretty good summary of why black holes are hard to see. They're very black. They don't emit significant radiation that you could reasonably pick up, and space is also black. It's like trying to sort of spot a raindrop in contrast against the ocean. You can't do it. There's nothing that stands out about them. Except, of course, as I was showing earlier, they do have these accretion disks surrounding them, particularly these supermassive black holes. This one here, as I mentioned, is a sort of rendering of Sagittarius A star, the black hole, the supermassive black hole thought to be at the center of our own galaxy. But the problem is, although you can see these bright sources, well, you can't even see them, but what I mean is you can detect like radio waves from these sources. That's how people first recognized that the nucleus of our galaxy was an active thing. Although you can detect it, you then can't zoom in and see the black hole at the center. Actually, the fact it's got all this stuff around it makes it even more difficult to see, because you've got this tiny little black pinprick that is surrounded by this incredibly luminous radiation. So it makes it even harder to detect the black hole in a way. So there's one way we've been able to spot black holes, that I'll talk about first, which is through gravitational radiation. And this is very recent. This is, I think it was the 2017 Nobel Prize, maybe 2016, I can't remember. What happens to information or matter when it passes through a black hole? Well, that is a difficult question. So at the moment, we're just setting up the sort of what is known about black holes astrophysically, not on a kind of very zoomed in scale about what happens to them. So today we're just thinking about the basics of black holes, which is still not very basic, but we're going to be thinking about the effect that black holes have on time, and the effect they have on light that passes by them. So we'll talk about how you would experience time if you were approaching a black hole, if you were near a black hole compared to someone that was far from a black hole, and we'll talk about how light is deflected around a black hole, as you can kind of see here. So from above, this thing is like it's in one plane. You've got the accretion disk in one plane spinning around, but if we look at it from the side, you can see that the light is kind of bent around it. The black hole acts like a lens, gravitationally bending the light around it. So that's another effect we'll talk about. But in terms of things like information in black holes and what goes on within black holes, I think we're going to leave that for another time. But also this is incredibly complicated and not particularly well known. We can talk about what happens as you approach the event horizon. Well, actually, you can talk about what happens when you pass the event horizon too. It's just that that information can't be communicated. But there's nothing particularly special about the event horizon. The event horizon is a sort of artifact of your coordinates. You can get rid of it by a coordinate transformation. Well, you can't get rid of it, but what I mean is you can describe sort of the interior of the black hole as well. You just can't describe the space-time singularity at the very center. So I will defer that question, if you don't mind, a little bit, and we'll probably come back to that another time. Okay. But let's go on a little bit and talk about detection of black holes through gravitational waves. So as I was saying, this first LIGO detection, I think happened, I know happened on the 14th of September 2015. I can actually remember the day it happened. Well, the day it was announced. It was announced, I think, in something like March 2016. So that was a very exciting day. But as for the event that happened, the thing they detected, the particular event they detected was two black holes, and he said black moles, black holes spiraling in towards each other and eventually merging to form a bigger black hole. And I think these two black holes, I wrote it down later on, they had masses of something like 30 solar masses and 35 solar masses, respectively. And as they kind of spiral in, I've sort of sketched here what this looks like. So in Einstein's picture of gravity, which we'll talk about in more detail shortly, gravity is modeled as a kind of bending of space-time. Okay. You have it on good authority that matter and information turn into turtles once inside a black hole. I mean, you may well be right. Who knows? So we think of gravity as a sort of as this bending of space-time. Okay. So I have the black hole, which I've drawn in yellow just because, well, as the problem with observing black holes is, if I draw in black on a black board, you can't see it. So they each have this kind of space bent in around them. And as they move in towards each other, they create regions of greater curvature between them, and they will sort of warp all the space between them. And then as they kind of merge, so the closer they get together, the faster and faster they are spinning around, spiraling into each other. And this creates an enormous amount of warping of space-time. And this warping is all dissipated as ripples in the space-time as they are merging and after they've merged. So these blue lines here are what I indicate by gravitational waves. Turtles all the way down. That's a good reference. Nice. And I've drawn these ripples as kind of ripples in the... I've drawn these gravitational waves, as kind of ripples in the coordinate grid that we're describing our black holes in. Okay, this is just an illustration. But the point is, if you produce these regions of high curvature, specifically if you produce regions of high curvature in a non-spherically symmetric way, then you produce gravitational waves which radiate out at at the speed of light. And we were able to detect these gravitational waves. This is what LIGO did. So, and yeah, there you are. So the particular event they had that they detected in 2015 was two black holes spiraling in towards each other and eventually merging, one of 30 solar masses and one of 35 solar masses. And when these things collided, the amount of gravitational waves that they emitted, the energy that that corresponded to, is 3 solar masses worth of mass energy. So in other words, you take the mass of 3 suns, times it by the speed of light squared, and that's how many joules of energy you have, which is a humongous amount of energy. That's more energy than the sun will. Well, it's more energy than, even as a lowest guess, it's more energy than 3 suns could ever produce. But it's significantly more than that. It's more energy than, many thousands of suns would ever produce. It's an enormous amount. High curvature due to high masses, right? Yeah, so it's due to not only large masses, but also masses in very close proximity to each other. So black holes, a single black hole produces a very large amount of curvature, around its event horizon. So black holes that are spiraling in very close to each other produce an even larger amount of curvature in between them, which is what sources these enormous gravitational waves, like the one we were just talking about. Okay. And then even more recently, there is a history of direct imaging. So you probably saw this image, which went viral on the internet, a year or two ago, which is the first sort of direct imaging detection of a black hole. And I still don't really know how they actually did this. It all seems very bizarre, the sort of technology and the software and the data analysis they had to do to actually get this picture. And it's completely out of what I know, but it's fascinating and incredible that they managed to do it. So here, in fact, the thing we're looking at around the edge here is this accretion disk, or material that is spiraling into the black hole that we can see, just like we sketched up here, not here, up here, this sort of luminous, high energy material that is falling in very quickly to the black hole. Can we apply the inverse square law to the black holes too? Well, so the inverse square law, this is Newton's gravity, Newton's idea of gravity. And Newton's idea of gravity does break down when we start to think about black holes. In fact, the next thing we'll talk about, once we've finished talking about the direct detection, is we'll talk about a precursor to black holes that actually does come from Newton's theory, that is sometimes called dark stars. And these were first written about in the late 1700s. So this is purely from Newton's theory. And in fact, if you do the calculation where you would like to calculate using Newton's theory the radius of a black hole, or more specifically the radius of one of these dark stars, you do get the same result you get from general relativity. So surprisingly, it does give you something quite accurate. But black holes you can't really describe. Not very near them anyway. You can't describe with Newton's laws. If you're very far away from the black hole, it's close enough. I mean, a lot of things at a great distance do become approximately describable using Newton's law of gravity. But for all the interesting stuff that goes on with a black hole, Newton's law of gravity misses out an awful lot. Okay? But you can use the inverse square law, if you like, to think about why it is the curvature is larger nearer the black hole than it is further away. Because, from Newton's theory, if you're very near to a mass, then you have a higher force there, because it's 1 over r squared and r will be smaller. And what we've said is that instead of thinking about gravity as a force, as when we talk about general relativity shortly, instead of thinking about gravity as a force, we think about it as curvature of space-time. So you can use that to kind of hand-wavingly deduce that you need, if you're very near a black hole or very near a mass, you have more curvature, more space-time curvature. Okay? So let's talk about dark stars. This was this next thing I mentioned that is quite relevant to your question. Okay. Oops. Dark stars. So this is a purely Newtonian prediction. This is not describing a black hole per se, this is describing the kind of Newtonian version of a black hole. So I think this was first sort of thought about, I can't remember who thought about it, but I looked it up and it was from around 1783. So this is massively before, you know, the kind of renaissance of black holes in the last century. And the calculation we do is we basically think about escape velocity. So if you're on the Earth, there's a certain speed. Now I can't remember what the speed is. You could work it out, but there's a certain speed that objects need to be traveling at, such that they can freely escape from the Earth's gravity. Okay, and we call this the escape velocity. It's the minimum speed an object needs in order to escape the influence of another body's gravitation. Okay, so if you think about it classically, no general relativity, just ordinary Newtonian theory, well, we can think about how massive or how dense would something have to be such that the escape velocity to get off of it would be the speed of light. And then you can imagine an object like this would look very dark, because if even light doesn't travel fast enough to get off of it, then we wouldn't expect this object to be emitting any light. So this is before even any idea of relativity or any idea that light sort of places a speed limit on the universe. This was just a thought. I can't remember who had it, but it's just a thought that if you had something that was massive or dense enough, even in Newtonian theory, you could have it such that light wouldn't be able to escape it. So let's think about... Ooh, why can't I draw circles? That's an oval. Let's think about this. So let's say we want to launch some small mass m off of the surface of some much larger mass, big M. And I'm going to give this large mass a radius, big R. And we want to know how fast to launch this smaller mass, V, such that it will fully escape the influence of the larger mass's gravity. And what I mean by that is it will reach R tends to infinity. Okay. And if we're looking for the minimum speed that you have to launch this thing at, such that it will reach R equals infinity, the minimum speed will correspond to when the velocity out here of the particle is equal to 0. Because if it had any larger velocity still in this direction, then we could have always given it a little bit less of a push down here, and it still would have reached infinity. It would still have some energy left over. So this is our setup. We've got two pieces of information. We have the particle on the surface that we're launching off of the larger mass, and we have the same particle later on a very, very large distance away from the big mass with no speed. And if we write the conservation of energy for this particle, we've got the initial energy of the particle. Well, here on the Earth, it's got kinetic energy. Well, sorry, this is not necessarily the Earth. Here on whatever body this is, the small mass will have kinetic energy. And it will also have some gravitational potential energy. Okay, given by this. Then if we think about out here, what energy it has, well, it has no kinetic energy, as its speed is 0, and as it's now pretty much completely left the influence of the gravity of the larger object, it's gone all the way to R approaches infinity, it will also have no potential energy. So the final energy is actually 0. And we know energy is conserved, so E initial is equal to E final. And we therefore have half little mv squared is equal to G big M little m over, that should be a capital R. Okay, this should be a capital R here, just because the object initially starts out a capital R distance away from the center. Okay. I just forgot what I called that radius initially. So you'll notice that we can cancel the two small m's. And then we can rearrange for v. So v, again, remember, is this minimum speed we have to throw this small particle off with, such that it will reach a very far distance away from the larger mass, and will have no speed when it gets there. So this is the definition of escape velocity. This speed here we have to throw it away at. So we say that the escape velocity squared, I'll say, is given by 2g big M over r. Okay. And now the thing these people said back in the 1700s was, well, how massive or how small does something have to be such that even light can't escape it, such that light, its escape velocity is light. So none of the light that would be emitted from the surface would leave the surface. It would all just sort of come crashing back down eventually. Now again, this is a 1700s calculation, so it doesn't suggest anything about how light and gravity interact, which before Einstein it was thought that they didn't interact. It was thought that because light has no mass, that it wouldn't be affected by gravity. So this is a very naive, 250-year-old calculation. But if they set the escape velocity of this body, whatever it is here, to the speed of light, then we rearrange for r. Okay? So if we rearrange for r, we get this formula here. And this formula describes a dark star, as it was called. So it says for an object of mass m, if you compress this mass m down such that it has a radius given by this expression here, then the escape velocity to get off of the surface of that object will be the speed of light. So in other words, it will appear completely dark because no light can escape from its surface. And interestingly, this result here actually also comes when we look at general relativity. So this will turn out to be the Schwarzschild radius of a black hole, or the size of it, the radius of its horizon. Okay, and you can get the same result, although in a totally not good way, from Newtonian physics, which is quite interesting how these things kind of come out, but not wholly unexpected. Okay. All right. So the next thing we want to do is we want to think about a slightly more sophisticated view of gravity. Okay. So now we're thinking about an extreme crash course in general relativity. Really what we'll do is we'll just motivate some of the mathematics that appears, and then we will just state some results. So we'll state the particular results that apply to black holes, and then we'll use these results to derive, well, at least one, possibly two things. We'll use it to derive this time dilation due to gravity. So how, if you are very near to a black hole, time will actually move more slowly for you than it will for someone that is further away from the black hole. And we'll also try and derive this deflection of light that is responsible for gravitational lensing around black holes, which was the first thing that was actually seen as a sort of experimental proof of general relativity. The first thing that was observed was, I think it was during the solar eclipse of, I can't remember which year, maybe 1917 or something. There was a solar eclipse anyway. And of course, when the sun is eclipsed, you can see sort of things in the background of it. So they were able to tell that the positions of stars in the background of the sun were slightly deviated from where they should be, and this deviation corresponded exactly to the bending of light that was predicted by general relativity. So this was the first experimental or observational test of general relativity. But rather than we talking about that first, before we talk about the bending of light, we have to summarize a little bit what we actually mean by general relativity. So there is one very important principle at the heart of general relativity, and this is called the equivalence principle. Now, there are lots of different ways of stating it, but the way that I want to state it is that free-falling objects, or free-falling observers, feel no effect of gravity. Now, think about if this makes sense. So, by free-falling, I mean not supported by anything. So, if you go up in, there are these plane trips you can do on Earth, where these planes will fly up to a very, very high, as high as they can in the atmosphere, and then they will kind of come down and free fall. And because they're free falling, they're falling at the same acceleration that the Earth is trying to pull them down at. People inside, you've probably seen clips, feel completely weightless and they kind of float around. Okay, so it's because these things are in free fall, they feel that the observers that are inside of this craft that's in free fall feels no effect of gravity. So this is an important principle, that if you're in a free-falling reference frame, so if you are free to fall under the effects of gravity, you will feel no effect of gravity. Okay. Now you can be more precise about this, and you can talk about the strong equivalence principle, which sort of refers specifically to local observers, because there are forces, there are ways you can tell that you're being affected by gravity, even if you're free falling. And these are what we call tidal forces. So not only is the gravity around a black hole very strong, but also the rate at which the gravity changes is very fast. So you can think about this just in terms of Newton's equation. So Newton says that the force of gravity when you're a distance r away from something, from a mass, is given by 1 over r squared. And therefore the rate of change, how quickly the gravity changes as you move inwards by some radius, is like r cubed. Okay? So if you get very, very close to this point mass, the centre of mass of this thing, which for black holes, because they're so dense, you can get a lot closer than you can for other things. Okay? Then the strength of the gravity also changes very, very quickly, which means if you're falling in kind of foot first towards one of these things, the gravity that your feet feels is much, much stronger than the gravity your head feels. And people often talk about this process of spaghettification, where as you're falling into these extremely strong gravitational fields, which also change very quickly, so getting slightly closer, when you're already very close, I should say, when you're already very close to the black hole, getting just a tiny bit closer corresponds to an enormous increase in the strength of the gravitational field. And because of that, the part of your body which is closer to the black hole feels a much stronger force than the part of your body that is further away from the black hole. And this causes people, this could cause you in theory to sort of stretch out, to be pulled apart a little bit by these very strong tidal forces. So when we talk about the equivalence principle, generally we should be a little more careful and talk about very, very small observers, because of course if you were big enough, if you had some sort of size, you would be able to tell that you were falling in a gravitational field because your feet would be pulled more than your head or something. But if you're very, very tiny, then it's like, you can say the difference in the force is this derivative of the force times your length. But if your length is very, very tiny, then the change in the force is very, very tiny, so you don't feel it. No, we didn't do df by dt, we did df by dr, sorry. So, of course, this could be, you could relate this to df by dt, because your radius will also change with time, but this is just showing how the force will change between two different points. So, if here is the center of your mass, whatever it is, the black hole, whatever it is, if first you're at this radius, r2, and then you go down to r1, then it's saying it's looking at the rate of change of the force you would feel as you move between a larger radius into a smaller radius. Okay? This was just a comment anyway, to say that when you're really thinking about the equivalence principle, you should be careful to say local observers, or very tiny observers, thinking about it like that. Okay, but the equivalence principle, the way we've stated it, it allows us to equate gravity, or the effects of gravity, with free-falling observers through space, or paths through space. Okay, so this is it's a bridge in a way. The equivalence principle is a bridge between paths through space-time, so the path someone takes when they're free falling, to the effect that gravity has. Okay, so think of an example. Think of the plane that is, these planes that go up and let you experience zero gravity. If it goes up to the top, simplify it. Think of it as an elevator. So it's just a room that is hoisted up to a high height in the atmosphere, and then is completely let go. So it's allowed to fall totally freely. What we've done in saying that free-falling observers will feel no gravity, so the person that is falling in this lift feels no effect of gravity, we've sort of related the effect of gravity, or rather we've related the absence of the effect of gravity with the path that this elevator takes as it falls downwards. Okay, so there is some relation between the effect of gravity, the feeling of gravity, and the path through space-time. Okay, very roughly, this is what we mean. It's some link between the two. And we call these paths through space-time geodesics. Okay. So we're throwing out a lot of kind of terminology. But this is just sort of motivating how we should start thinking about general relativity. So if we have some curved space, okay, this is some kind of, I've drawn these as like coordinate grids that are kind of bent. So this looks like a sort of warped space-time. Then the geodesic is the path that sort of follows the warping of this space-time. Well, it's the path that connects 2 points in this warped space-time that extremizes the kind of 4D version of length. If you've seen special relativity, you've seen this interval, this invariant interval, which is kind of our relativity version of length, where we no longer just think about length in space, we have to think about length in time. And we want to, this path that particles take will be extremized, so it will be minimized or maximized. And the particular path depends on how curved this space in the background is. It depends where what the specific curvature is will affect how the path is, okay? So in other words, well, to summarize, the geodesic path will depend on the curvature of the space-time. Okay. So we've said that there is a link from the equivalence principle between the effects of gravity and the path that objects take through space-time, these geodesic paths, okay, of a free-falling observer. So that allows us to kind of roughly say gravity is roughly equivalent, this is not any mathematical equal sign, this just means gravity kind of arises from curvature of space-time. That is the logic we're using to present that fact, that gravity can be related to the curvature of space-time. Okay. What else do we know? We know from ordinary Newtonian We know from ordinary Newtonian gravity that matter, mass, produces gravity. And we know from special relativity that energy and the mass of objects are sort of interchangeable. They're not independent of one another. They're related most straightforwardly by E equals mc squared. So not only does matter source gravitational fields, we say that matter and energy will source gravity. Gravity will produce energy, or gravity contains energy within it. This is also obvious from Newton's theory that there is such a thing as gravitational potential energy. So gravity carries energy within it, and matter and energy will both produce gravitation. Okay. So now what we're sort of doing is we're taking these two, very schematic, rough equations, that gravity is roughly given by curvature, and that matter and energy will source gravity. Okay, we know, no, don't worry, we're not going to dive into quantum physics today. This is all still classical. General relativistic, but still classical. So matter and energy source gravity, and gravity can be thought of as curvature of space-time. So this allows us to write down the absolute most basic way of describing general relativity, or describing Einstein's equations, which is that the curvature of space-time is roughly equivalent to matter / energy in that space-time. Okay. But we can already think about how this is slightly different already from Newton's idea of gravity. So in Newtonian gravity, if you have a part of space which has absolutely no matter in it, there's no matter anywhere nearby, then that means you have no gravity. If you've got no matter, there's no big M in your inverse square law, so you've got no gravity. But actually, Einstein's gravity doesn't necessarily say that, because we can also have energy producing curvature, i.e. producing gravity, and gravitational fields themselves contain energy. We can have gravitational fields producing other gravitational fields, okay? Curvature producing other curvature, which is exactly how these gravitational waves kind of propagate. Just like electromagnetic waves will propagate themselves, that electric fields produce, or changing electric fields produce changing magnetic fields, and changing magnetic fields produce changing electric fields. Well, the curvature of space-time is itself a source of curvature of space-time. So Einstein's gravity is highly non-linear, and it has built within it the prediction of these gravitational waves, though we're not going to do any maths on these gravitational waves just yet. Well, or today, in fact, maybe another time. But you can see how there's some logic that we might expect them to be there. Okay. So how can we make this more concrete, this mathematics? At the moment, we have kind of a schematic form of what will become Einstein's field equations. We have that the curvature of spacetime should in some way be linked to the matter and energy distributions within the spacetime. Okay. So in special relativity, we describe matter-energy distributions by a tensor, which if you haven't seen any special relativity, you might be a little scared by the idea of a tensor. And I'm not going to say too much about it now other than it's a tensor, because if we have to talk about exactly what a tensor is, we'll be here a very long time. Okay. So this tensor here we often call the energy momentum tensor, or sometimes the stress energy tensor. I'm going to call it the energy momentum tensor. And this encodes within it matter and energy distributions. Okay. This is how we describe energy distribution. Well, no, not like a Boltzmann distribution. Not like. So that is more about. That's about how the energy of individual particles is distributed. So if you have a very large number of particles, the Boltzmann distribution tells you, what speed you expect a certain fraction of the particles to take. This is more about, when I say distribution, I mean how the matter is distributed through space. Okay, so like, say in a star is a spherically symmetric distribution of matter, because stars are spheres. They're at any single radius within the star, your properties, your matter distribution, your density, etc. is really the same. So it's about how the matter is distributed in space, where we put our matter in space, where we put our energy in space, all of that kind of thing. That's what I mean by distribution, okay? So as a mathematical note, we note that this is a rank 2 tensor. So describing our energy and matter distribution in this way is sort of an inspiration from special relativity. Okay, this is how we would describe things in special relativity in this tensorial way. Okay, so now we've got a kind of tensorial description of matter/energy, and we want it to be, as another note, we want it to be tensorial as sort of inspiration from special relativity, in that we don't want our description of gravity, our physics, to depend on a particular coordinate frame. And tensors as mathematical objects are very useful in that they transform in a particular way. That means that they are not dependent on the coordinate system you use. They transform in such a way that when you change coordinates, the form of the tensor stays the same. Okay. The only thing that changes is the coordinates you're describing it in. But the issue we run into now is that there are actually multiple ways to describe curvature as a tensor. Now, we know that if we're going to try and reproduce this schematic equation here using more concrete mathematics, if we've got our right-hand side is our tensorial description of matter/energy distributions. Then the right-hand side being a rank 2 tensor, the left-hand side should also be a rank 2 tensor, okay? Just like if you write down a matrix equation, if the left-hand side of your matrix equation is 3 by 3, you want the right-hand side to be 3 by 3, and so on. So we need a rank 2 tensor that describes curvature. The first one that Einstein tried, so I think this is October 1915. Einstein wrote this down. He wrote down this tensor that is called the Ricci tensor is roughly equivalent to the stress-energy tensor. So the Ricci tensor here, this is a description of curvature. It does describe the curvature of a space, of a manifold, and this follows the same schematic form as our equation up here that we motivated earlier. But there is one issue. So from special relativity, so I should say that this is wrong. From special relativity, we have that the divergence of the stress-energy tensor should be 0. Okay. And within it, if you work out all of the components of this contains statements about conservation of mass, conservation of momentum. You can produce from this in special relativity the Euler equation, which describes conservation of momentum of a fluid, and you'll also get a conservation of, or a mass continuity equation. So that, a mass continuity equation looks something like this. So like your total matter is like the volume integral of your density. Although it would be in differential form, so it would be more like, well, I can't remember the exact form now. It doesn't matter anyway. That's the rough form it would take. It would contain these statements, these pieces of information. And when we take this to GR, so in GR, derivatives like this, derivatives just with respect to the coordinates, are not actually very good. Okay, so we want everything in our equations to behave as a tensor. We want it to transform and keep its same form when we go to any coordinate system. But you can show that if you try to transform an ordinary derivative in general relativity, you don't get the same exact form. You don't get this derivative just in a different coordinate system. You get a different tensor entirely. So in GR, we replace these ordinary derivatives with what are called covariant derivatives. And this is just a derivative that takes account of the fact that in order to compare two different vectors or tensors that occur at different points in your space-time, you have to sort of transport one of these vectors in a consistent way to the other in order to compare them. So you have to compare the vectors in a way that gets rid of this natural change in the vectors if you were to move them through this curved space. Okay, this is a little complicated. But anyway, the point is we replace these ordinary derivatives with what are called covariant derivatives. So this is called a covariant derivative. Okay. So we expect that this should be true in general relativity. This is like the general relativity version of what is included in here, which is conservation of momentum and mass continuity. So it should be true that if I take the covariant derivative of the right side of this equation, I should get 0. But then if these things are really equal, I should also get 0 if I take the covariant derivative of the left side of the equation. But, unfortunately, this is not in general true. So this kind of guess Einstein had for this particular form of his equations violated this condition, which is very well motivated and expected that this condition should hold because it contains conservation of energy, conservation of momentum, all of those things that we know are important. So what we need in order for this equation to remain consistent and to have our general schematic equation that curvature of space-time should in some way be related to the matter/energy distribution, we need to find a rank 2 tensor such that the covariant derivative of this tensor is 0. And that'll give us the left-hand side of Einstein's equations. So if covariant derivative is 0, that means it's linear or tangential. No, well, so it depends what you mean by tangential. So it means if you parallel transport, so the idea of these covariant derivatives is a little difficult. It sort of means you have to drag one of these vectors along through the curved space to compare with them. Maybe. So they'll if the covariant derivative of a vector doesn't change, it means that once you've parallel transported it back to the other point in the space, it's not changed. But they may well look different when they're at these different space-time points. Okay. This is a very kind of hand-wavy introduction to general relativity. General relativity, usually if you were to do a course on general relativity, it would be like 20 hours or something, and then you would get up to this maybe an hour 10 or 12 or something. So this is an extremely quick introduction to general relativity. So we need to find a rank 2 tensor such that its divergence, or rather the covariant derivative of it, will give us 0. Okay. And there is actually something that was known at the time that would give this. So all the way back in 1889, we have this so-called differential Bianchi identity. So, you know, this existed 30 or so years before Einstein was trying to look at these things. But this was very sort of niche mathematics that was not known to really any physicists and not even known to many mathematicians, I think. It's an example of when the mathematics has preceded the physics, which still happens, you know, still happens quite a bit. There are lots of parts of mathematics that are not used by physicists today that may well be used, or, you know, or rather, there are lots more that were unused in the last 30 years, but in the last 30 years after that have been picked up by physicists. Okay. But this fact from differential geometry anyway says that the covariant derivative of this particular combination of tensors and scalars will always give 0. Okay. Unfailingly, this will always give 0. Where we take, or we understand this R here to be the trace of the Ricci, or the contraction of the Ricci tensor. And G mu nu here is the metric tensor. So I'm not explaining every part of this because, as I say, this is like a lightning speed motivation for general relativity. So then somehow, I don't know if Einstein ever actually, he was told this identity or how he came to it, but anyway, if he'd had this identity, he would have been able to do it a lot quicker. But with or without this identity, he came to this equation, where G mu nu is precisely this tensor that covariant derivatives to 0 from before. Okay, so that is the kind of, that's a rough presentation of the sort of logical chain of events and ideas that led to Einstein writing down this equation. I mean, of course, he wrote it down as G equals, and then he had a constant here, and he didn't know what the constant was. So then he had to figure out this proportionality constant between the two sides of this equation. And he did that by looking at the limit in which general relativity turns back into Newtonian gravity. So in this very weak field limit. Okay. And by doing that and comparing what proportionality factor constant he should have here, he managed to write down this equation. Where c is the speed of light, g is Newton's constant, and then this is sometimes called the Einstein tensor. But it's just this combination of the Ricci tensor and the Ricci scalar we showed above here. Okay, that comes from this Bianchi identity. And then the right-hand side here, again, is encoding the matter-energy distribution within the space-time. Okay. So this whole thing, or these whole equations, are called Einstein's field equations. And these describe how matter bends space, how matter bends space-time, and how space-time affects the path of matter. This is the matter side, the matter-energy distribution side, and this is the curvature side. So this does follow the same schematic form as that very rudimentary equation we wrote down all the way up here, that we expect the curvature of space-time to be somehow related to or equivalent to the distributions of matter and energy in the space-time. Okay, so this is a presentation of how Einstein, how you could arrive at Einstein's equations in this way. But these equations that are contained within these tensors are incredibly complicated. So G mu nu, which remember has this r mu nu and this r part here, these are second derivatives of the metric tensor of g mu nu. So overall, this equation is some second order nonlinear partial differential equation. So an incredibly difficult differential equation to solve. You wish schools taught Einstein's physics laws. Well, this would be a difficult one to teach in school, definitely. They teach this in universities. There's not even till a pretty late time in university, really. Usually at your third year at the earliest, you can study these things. But special relativity is a little more accessible. You could definitely learn special relativity in school, and I think some high school, A-level high school qualification physics syllabuses in the UK actually do have that on them, which is very nice. So this was now, so Einstein, I should have said, Einstein wrote this down. This is now November 1915. So this is a month after he wrote down the slightly incorrect version with the Ricci tensor. This is now November 1915. He got this much more correct form that eventually was even corrected even more with this factor at the front here. Okay. And pretty soon after, so now forward to December 2015, a physicist and mathematician called Carl Schwarzschild, and he actually published this work while he was in the Second World War, in the First World War, in the German trenches, and he died very soon after he published it, very tragically. He wrote down what is called the Schwarzschild solution, or Schwarzschild metric, we'll call it. Okay. And this solution describes the space-time outside of a spherically symmetric matter distribution. And we've looked at the Schwarzschild metric a little before. So when we spoke about, for any of you that were here when we spoke about Mercury's orbital precession, we used the Schwarzschild metric a lot then. When we used it then, we were using it to describe the sun. So this doesn't just work for black holes, although we're talking about black holes today. The Schwarzschild metric describes any spherically symmetric distribution of matter. So, that could be things like planets, although planets are not really massive enough that it would be useful. You could just use Newtonian gravity for planets. Things like planets, stars, black holes. These are all described through this Schwarzschild solution. Okay, and we'll write it down. And the form that we'll write it down in is in terms of this invariant space-time interval. Okay, so the thing, when you solve Einstein's equations, the thing you solve them for is this metric. We could link to entropy. Well, we're not going to talk about black hole entropy today. Certainly that is an interesting topic, but we're only going to cover kind of the introduction to general relativity and a few results we can get from general relativity. Okay, possibly only one result. We might just do time dilation today, I think, and then maybe sometime either next week or the week after. Because I'm quite anxious, actually. I'd quite like to talk about white dwarfs next week. I fancy talking about white dwarfs in the next Saturday Spacewalk. But maybe the one after that we can do a follow-up black hole thing, where we'll talk more about information and entropy in black holes. But for today, we're just going to try and focus on getting time dilation out of Einstein's equations. Okay? So when we solve Einstein's equations, we solve it for the metric, this g mu nu term. But there's another way we can write it. We can write the solution down in terms of the invariant space-time interval. Okay. So remember from special relativity. So in SR, this invariant space-time interval looks like this. It's just kind of a 3D Pythagoras term, but then there's this non-Euclidean sort of minus part in the metric. Okay, good night, Sohail UAE. But for the Schwarzschild solution, this metric is a little more complicated. Now we're not dealing with flat space-time, we are dealing with curved space-time. And the solution now looks like this. So this RS here, I'll explain what this means in a minute. RS is actually the Schwarzschild radius. So this is this same number that we came to when we were looking at dark stars. Okay. This 2gm over c squared. Okay. So let's comment on what this actually means in terms of coordinates. So we've got this term here, which is like a spherical polar coordinate term. So as usual, d omega squared is short for d theta squared plus sine squared theta d phi squared. R is a radial coordinate, and theta and phi are angular coordinates. So we have our black hole, or whatever it is, here. Then labeling some point here is labeled by a radial coordinate measured from the center, that I'll denote R. Then one angular coordinate, theta, measured from the z-axis. And then a second angular coordinate, which is measured between the shadow of the orange line, on the xy plane, against the x-axis. Okay? And then the time coordinate. So the time coordinate in the Schwarzschild metric is the clock time measured by someone very far away from the black hole. Okay? That's how we define it. And like we sort of did when we thought about Mercury as well, we can equate this invariant interval, because the point is this will not depend on reference frames. Just like in special relativity, this reference frame is invariant. Okay? This is equal to the proper time that will be measured by somebody moving in this space-time. Okay? That is something we will use later that will be useful. So here's our metric. Now we're going to try and take this metric to get to an expression for time dilation. Okay? Okay. So let's write down part of what we had before. We have this space-time interval where I'm going to keep this d tau squared on the left because this will be important, which is equal to this form here. Oh, I feel like I missed a c squared above. No, I didn't. Oh, okay. This form here. Okay. So let's think about two separate observers, some distance away from a black hole. Here is the center where we'll measure our radial coordinates from. let's put the first one at distance r1, and the second one with their clock there at distance r2. Okay. So let's think about the time interval measured by person 1 here. So this is person 1, and this is person 2. So let's say that person 1 measures some time interval delta tau on their clock. Delta tau 1, in fact, to keep the number there. And we assume that for the same event, the same time difference between two... okay, let's think of it differently. So there's some event that happens. Maybe this is just they're looking at their watches to see things tick around. So person 1 sees a tick on his watch take delta tau 1. Okay, and between the same two events, person 2 will measure delta t2 between ticks on their watch. Okay. Then we also have this coordinate time that we've called t above. This is the t that appears in the Schwarzschild metric. So this is the time measured by a clock that is very, very far away from the black hole. Okay. And now we can just use our invariant interval to get some equations that link delta tau 2 to delta t, and also delta tau 1 to delta t. And then from those we can link delta tau 1 to delta tau 2. Okay. Hello, Machu D Pariah. Okay. So from the invariant interval, remember tau is this proper time, the time that is measured by an observer at a fixed point in space. Okay. So for this observer fixed at this point in space, the time that they measure on their clock is this proper time. Okay. So we can say, thinking from person 1's perspective, we have minus c squared delta tau 1 squared. And this will now be equal to what is on the right-hand side here. But the coordinates of person 1, well, his radial distance from the black hole is r1. He's not moving, so his delta r is 0. He's not changing his spatial position, and he's not changing his angular position. So the only thing that changes is this dt here, which, remember, is the time measured by the coordinate clock. This is a very large distance away. So we have this equation. Okay. And then we can write the same thing for person 2 as well. Where now person 2's radial coordinate is at r2. Okay. If you want to be very concrete with this, you can think about person 1 sending sort of a succession of light pulses out to person 2, where maybe between their first and their second light pulse, person 1 measures a distant difference in time delta t1. And then we think about when these light pulses reach person 2, what is the time difference between the pulses that person 2 measures? And we can use that to figure this out. Okay, but this way is a little less concrete, but it works just as well. Okay. And now we can cancel these c squareds here. And we can use this equation in terms of delta t squared to write delta tau 1 in terms of delta tau 2. Okay. And if you do that, if you write it all out, you get that it's all equal to quite a sort of long expression. but it's the square root of this entire thing times by delta tau 2. Okay. So if person 2 measures some period of time between events tau 2, then person 1 will measure the same a different period of time delta tau 1 between those same events. Okay. And you can see that because R1 is smaller than R2, the denominator here will be smaller than, sorry, the numerator here will be smaller than the denominator here. So we have that delta tau 1 will be less than delta tau 2. Okay. Because this thing here is smaller, therefore this term up here, this whole thing, this RS over R1 will be bigger. It'll be closer to 1, because also the radius is always outside of the Schwarzschild radius. We're not thinking about things inside of the black hole. Therefore, this term up here will be smaller than this term up here. So delta tau 1 will be smaller than delta tau 2. Okay, so we've shown that black holes do change the passage of time. We've shown that the closer you are to a black hole, the less time you experience, the slower that your clock will tick. You've heard that near the horizon it takes infinite time. Is that delta tau or delta t? That's delta t. So for someone that is falling into the black hole, if you're trying to find the time it takes for someone to fall through the event horizon, as measured by delta tau 2, so the person, say person 1 starts falling in, they would measure a finite time for them to fall in, but person 2, delta tau, they would measure a very, very large time. Okay, they would in fact measure an infinite time for them to fall through. And that is also delta t. Delta t, the coordinate time, would also be infinite in that case. But that is an interesting point. Delta tau 1 would take a finite amount of time to fall through. They would pass through the horizon just fine without hitting any invisible wall or something. They would just pass through it. But delta tau 2, person 2 I mean, and the coordinate time for an observer at infinity would measure an infinite amount of time taken for that person to pass through the event horizon. Okay. But this result here is interesting, and it confirms what we were just saying just then, that the amount of time that is passed according to the person closer to the black hole is less than the amount of time passed by someone further away. So between the same two events, the person that is nearer the black hole would measure less time than someone that was further away from the black hole. So it's like the closer you are to a black hole, the faster time passes for everyone else, for everyone further away. Like how in Interstellar, when they're on the planet where they're near the black hole, everyone back on Earth, everyone a large distance away, gets much, much older. So that's like here, these are the people on Earth. They experience a much, much larger amount of time, whereas the people near the black hole, they experience a much, much smaller amount of time. So time passes. It's hard to talk about these things because you can say, well, you experience less time when you're near the black hole, but then it's kind of like time passes faster for you because more time has passed away from you, outside of you. But actually on your clock will tick fewer times than the clocks further away from the black hole would tick. So if you were falling into a black hole, you would see things outside of the black hole all happen very, very quickly and sort of unfold very, very fast around you. Whereas if you're looking at someone falling into the black hole, you never actually see them fall into the black hole. You just see them sort of approach it asymptotically and get closer and closer and kind of flattened on the horizon and redshifted as well. What about a photon? What about like a photon falling into the black hole? I mean, thinking about things from the perspective of a photon is hard to do. And really it's not well defined to do because you can't think of. So here what we were doing in these taus, these are proper times. So these are times measured in the reference frame in which person 2 is still. Delta tau 2 is the time measured in the reference frame in which person 1 is still. Okay, so it appears here as the proper time. But there is no proper reference frame for a photon. You can't boost into a reference frame where the photon is still because it's one of these central principles of relativity that the photon will travel at the speed of light no matter which reference frame it's in. So you can't get into a reference frame, the same reference frame as a photon. So you can't really sort of imagine what a photon sees. I think Einstein did sort of think about what you would see if you were riding on a light wave when he was first thinking about special relativity as a kind of thought experiment. But I've never managed to get my head around his explanation of what you thought you would see. And I think it's not a well-defined thing to think about, because you can't actually get in the same reference frame as a photon. Okay, but I mean, you can sort of argue that because photons are traveling at the speed of light, their time is so greatly dilated that they actually oh wait, hang on. So they experience all time sort of at once. So if you were to travel very, very fast, if you travel very, very, very fast, then everything else outside of you traveling very, very fast, you know, if I travel very, very quick on a rocket away from the Earth, when I come back to Earth, more time will have passed because I was traveling very, very fast. The faster you travel through space, it's like the slower you travel through time. So everything else happens much, much quicker outside of your ship. So from light's perspective, because light is traveling at the speed of light, it's like the entire universe kind of has just happened in one go, in one instant of time for the light. But that's not really a thing to think about, because these equations break down at the speed of light. But that's if you were going to try to think about what a light ray would see in that way. That's like what a light ray would see. A light ray would see the entire universe sort of unfold at once. But I'm not saying that's actually what they do, because the equations aren't good at going to V equals C. They're good at going to V approaches C, but V equals C, going to the frame of a photon, is not a good thing. You can't do that. Okay. But let's think about what happens in relation to that. Think about what happens as person 1 falls into the black hole. So as person 1 gets closer and closer to the black hole, so as the radius approaches the radius of the black hole. So now we're taking the distance of person 1 from the black hole to be roughly equal to the radius of the black hole itself. So that means this thing here is going to roughly be 1. Rs over R1, where R1 is becoming Rs, will be roughly 1. So we'll have a 1 minus 1 up here. So this whole numerator will roughly equal 0. So that tells us that the time experienced by person 1 will be roughly 0. Okay. Yet delta tau 2 will still be finite. So in other words, in the period of time it takes person 2, who is now away from the black hole, to experience some event. So the time measured by person 2 is some ordinary finite time, 5 minutes, whatever. Person 1, who is now just at the horizon of the black hole, would experience that same amount of time as measured by person 2, but they would experience it in practically no time at all. So they would see whatever person 2 would see to happen in 5 minutes. Person 1 would see it happen practically instantly. They would see much less time occurring than person 2 would see. Okay. So these things really do get crazy as you approach a black hole, which is why we sort of described what you would see if you were falling into a black hole, kind of looking out. What I think you would see is you would see everything outside of the black hole happening much, much, much quicker. Until eventually, as you sort of pass through the black hole, you actually see things kind of just sort of, you'd see the universe sort of pan out. It would all kind of happen. Time would pass very, very quickly as you would see it for everything outside of the black hole. Okay, but for someone watching you fall in, they would see you never actually fully fall through. They would see you get closer and closer to the horizon, but never cross it. Okay, so these things really are pretty crazy. I mean, we've talked today only about the most basic crazy bits about black holes, but there's so much more crazy stuff about black holes, which I think now I'm going to leave for next time. So there is a tiny bit more I was thinking of talking about this gravitational lensing, which is how light rays can bend black holes. And if you want to read about that, so I did write some notes on that you can find on my website, which is linked in my About section. Though the calculation I did, I got it slightly wrong. So the very end of the calculation, where I worked out this angle that the light ray is bent by, I got it a factor of 2 off. So if you're looking at it, it says RS over B, but it should be 2RS over B. And I can't find the factor of 2. If anyone can spot the factor of 2, I don't know, I'll buy you a cookie or something. I'm not sure. If you can find the factor of 2 in the end of the PDF, then I'll buy you a cookie. Okay. But yeah, I think we'll leave it there. And then maybe next week I'm thinking for the Saturday Spacewalk, we can talk about white dwarfs, which is a little diversion from this, but I am quite keen to talk about white dwarfs because they are very interesting objects. And then perhaps the week after we can come back and talk about black holes again. Okay. So here is just, for those that didn't see, this is a nice little rendering of the black hole at the center of our galaxy. That is called Sagittarius A star. So here you can see the accretion disk around the outside of this inspiraling matter. And then you can also see the jets that are coming out of this. And these are all generated in quite complicated ways that I certainly don't understand, and I don't think actually anybody fully understands at the moment how these jets are produced. So there's so much about black holes that still isn't known, and they are really fascinating objects. But I think we'll leave it there, and then next week we'll talk some more about white dwarfs, because that'll bring in some kind of quantum mechanics-y stuff as well, and try and figure out from scratch this famous result for the Chandrasekhar limit, this maximum mass you can have for a white dwarf. That'll be something interesting to figure out. And then perhaps the weekend after, we'll come back to black holes, and maybe we'll skip the bending of light thing, and maybe instead we'll focus on more sort of quantum-y aspects of black holes, talking about information and entropy, Hawking radiation, and we'll see if we can do some proper calculations with it. Because I like, when I do these things, I don't like just sort of stating facts. I think it's nice if you can give a route about how we can derive these things. Okay, so that's the plan. That's what we'll do next time. But we'll leave it there for now. In the meantime, if anybody wants to join my Discord, please do. The link is there in the chat. And yeah, let's leave it there. And I'll see... It's a place you can clear your doubts. Okay, awesome. And yeah, I'll see some of you on Tuesday for my office hour. And then Thursday for Mario Kart and physics chat. And then again on Saturday for another Saturday Spacewalk, where I think next week we'll talk about white dwarfs, which should be interesting. And I'm still thinking about some other things we could do in the week on different days. Maybe some more structured stuff, like go through a course or something, or work through a textbook together. So if you do have any thoughts on that, you can let me know on the Discord, and I'd be interested to hear what you have to say. But yeah, let's leave it there for now. Okay, thanks for coming, everyone. Bye, everyone. Bye.